So this is 13.34, and it says which of the following in each pair is likely to be more soluble in water. So first, what makes something soluble in water? Well, water, remember, is a polar molecule, so it's got a negative end to it and a positive end to it, and it's got a dipole moment that would go in this direction, and it would be capable of hydrogen bonding because it has an H connected to an F or N, making it a highly polar molecule. And since like dissolves like, what we want to be able to dissolve in water is something that's like water. In other words, it's polar, and maybe it has a smaller size because this molecule is not very big. I mean, it only has 3 atoms in it. It's 18 grams per mole, something like that. So small polar substances would dissolve the best in water. So let's look at each of the pairs. The first one is cyclohexane or glucose. So cyclohexane would be a circle like this, and then we'd have hydrogens all around it like that, a cyclohexane like this. Actually, there'd be 2 hydrogens coming off of each one because we got to have 4 bonds, and there are, as you can see right here, 12 hydrogens. Count them up. And you'll notice this is regular and repeating, and there's no specific place where it's asymmetrical. Perfect symmetry here, 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 here. And so this is definitely a non-polar molecule, very non-polar. Then the second one would be glucose, C6H12O6. And we can see from glucose, there are a couple different versions of it, but it definitely has C and OHs coming off of it. You can see O's and H's right here. One form of glucose is a ringed structure that has OHs coming off of it. Another form is 6 carbons in a row, and it has OHs coming off of it in multiple places. And since it's going to have these OHs coming off of it, it is going to have hydrogen bonding capabilities. And even though it's a little larger molecule, it has a lot of these OHs available, and therefore it can dissolve in water lots better. So we would choose glucose for letter A. Letter B, we have propionic acid or sodium propanoate. So in this one, we've got propionic acid, so you can see that this kind of tells you the Lewis dot structure. CH3, then there'd be a CH2, and then there'd be a C double bond OOH. That's what makes it be an acid, is the double bond OOH. The other one is got an Na attached to it, and notice the H is gone. And so we'd still have this CH3, CH right here, and then we'd have a C double bond OO, but this would have a negative charge to it now right here. And then the Na would be attracted to it, and this would make it be an ionic compound because we'd have this ion and this ion stuck together. You can think of this as one big giant polyatomic ion that's stuck together with the Na. Now I know that this one's got hydrogen bonding right here, but this one has got ions in it. And if you remember the list from the strongest to the weakest interactions, if you can have ion dipole interaction with water, you're golden, because that is like the strongest interaction you can have generally for dissolving. And so the sodium propanoate right here would be the better dissolver of the two. All right, on to letter C, HCl. So HCl would be a Lewis dot structure like this, where we'd have a negative charge here and a positive charge here. So we have a dipole moment in HCl. Or ethyl chloride. So ethyl chloride would be CH3, just like it's written, and then CH2, and then we'd have a Cl coming off of the end. And it looks like I'd still have a dipole right here going a little bit towards the chlorine. And then my choice is, which one's going to be the better dissolver in water? It looks like both would have a negative charge here, a negative charge here, a positive charge here. And so you probably have to go to the second criteria. Both are polar. Probably the smaller one, the more that's like water's shape, would dissolve better. And so you'd choose HCl right here as being the one that would probably be better at dissolving in water than the ethyl chloride right here.